Hello everybody, this is Dr. Christopher White, and in today's video we're going to be looking at the lab exercise plate tectonics and rates of motion. So as you can see, we have the dual document setup. So over here on the left we have the Word document version of the lab exercise, and over here on the right we have the PDF version. So the PDF version is open in Adobe Acrobat, so this is a program that you can download from Adobe for free off the internet. So like any of the lab exercises, it begins with a brief explanation of the concepts that will be dealt with within this lab assignment. Now, please, before you start this lab exercise, take the time to go and watch the plate tectonics lecture, because that's obviously going to address the concepts dealt with in this lab in considerably greater detail than the lab exercise will be able to do. So the lab itself begins with a discussion of Alfred Wegener's 1912 theory of plate tectonics, and this is a unifying model. So Alfred Wegener's model brought together several strands of data, and what it did is it produced an overriding explanation for each of these different data sets. So by having this grand model, it allowed each of these data sets to be explained. Whereas if you dealt with each of the sets individually, it would have been maybe difficult to come up with a solid explanation. As soon as you combine them all together, you can come up with one solid explanation as to what you are observing. So once Alfred Wegener did this, it became clear that the Southern Hemisphere continents, so in this case, South America, Africa, India, Australia, and Antarctica, were once joined together as a single landmass, which we now call Gondwana. So the pieces of evidence that were used by Alfred Wegener were the jigsaw fit of the continents, the stratigraphic fit, the tectonic fit, the glacial fit, and the fossil fit. And once again, each of these particular data sets is covered in much greater detail within the plate tectonics lecture. So for each one, as you can see, there's a brief explanation about what each dataset was showing and how that relates to Alfred Wegener's theory of plate tectonics. Obviously, I'm not going to go through it now because, once again, please watch the plate tectonics video. Okay, so on to part one. In part one of the lab exercise, we're going to be looking at divergent boundaries and magnetic lineations. So, following on from Alfred Wegener's 1912 work on the theory of plate tectonics, the next big step was Harry Hess's 1962 work, The History of Ocean Basins. So, his book dealt with observations that he had made of the seafloor from several different oceanic basins, with an especial focus on the Pacific. So Hess noted two main things. The first thing he noted is that along the margins of some oceanic basins you would find deep trenches, which we now know are related to subduction zones, and we'll obviously come on to those later in the lab. He also noticed that towards the center of most oceanic basins you would find a linear band of elevated seafloor terrain. So just to give you some idea, these elevated bands are about 1.5 to 3.5 kilometers higher than the surrounding abyssal plain. So Hess had to come up with a mechanism that would explain how you end up with this elevated terrain in what is otherwise a pretty flat and uniform topographic environment. So Hess went and explained this by suggesting that maybe there was a buildup of magma underneath these areas, and obviously the magma being buoyant, it wants to rise, and so it pushes up the crust directly above it, resulting in these linear bands of elevated terrain. Then obviously the next step is to think about, well, what's going to happen with this magma, and so Hess eventually came to the conclusion that these bands of elevated terrain may well represent regions of the seafloor where new seafloor is being made. And so obviously this is the first indication of the existence of divergent plate boundaries. Now, although it was a good theory, the problem is that he didn't actually have any direct evidence to prove that there was actually divergence, i.e. the creation of new oceanic crust and it being pushed laterally at these areas of elevated terrain. So that had to wait until the work of Frederick Vine, Drummond Matthews, and Lawrence Morley. So this work came out in 1963, so only a year later, so there wasn't a big gap. And their work focused on the polarity of magnetic bands in the ocean floor. So one of the things that we know about the Earth is that its magnetic field is not constant. The orientation of it will flip. And so at the moment we have a normal magnetic polarity, so north is north, south is south. But for periods of time that will actually reverse, and you will end up where periods when the magnetic polarity is essentially north is south and south is north. And one of the things that happens with rocks, especially basalts, is that as they crystallize, the magnetite, which is one of the minerals within a basalt, will grow and it will orientate itself parallel to the magnetic field at that time. So when the basalt is crystallizing in a normal magnetic field, the magnetite crystals will orientate themselves based on that normal magnetic polarity. And when the magnetic field is reversed, the reverse will happen. And obviously, once the basalt fully crystallizes and solidifies and becomes one solid piece of rock, these magnetite crystals, they can't move anymore. They're locked in that orientation. And so when you come along later with a magnetometer and you measure those rocks, what you're going to see is you're going to see these bands of positive and, should I say, normal and reversed magnetic polarity. And so this was the first indication that you have this divergence, this splitting of the oceanic crust at these regions of elevated terrain, these mid-ocean ridges. So if we look at the figure at the bottom here, what do we see? So we see our basic model where we have two pieces of oceanic crust and they're separated by this dark black dashed line, which represents our divergent boundary. So the first thing you'll notice is that either side of our divergent boundary, we have a matching pattern of normal and reversed magnetic polarity. So you can see at the moment, the oceanic crust being produced has a normal magnetic polarity. It's then reversed, normal, reversed, normal, reversed, normal. So you'll notice that the width of these bands is changing. Obviously, the wider bands represent longer periods of either normal or reversed magnetic polarity, and the thinner bands represent shorter periods of reversed or normal magnetic polarity. And so you'll notice that these bands mirror each other either side of this divergent plate boundary. And so what this evidence is showing us is that as new oceanic crust forms along the spreading ridge represented by the dashed black line, the new oceanic crust the magma is pushing up between the two plates. It's pushing them apart, it's creating new crust, and a new pulse of magma comes up, pushes them apart, creates new oceanic crust. And so over time, any crust that forms at the divergent plate boundary here is being split in two, and then it's being pushed laterally away from the divergent plate boundary. And now what's also happened later on is that we've been able to go to these locations with drill ships, and we've been able to drill down into the ocean floor, and we've also been able to date the oceanic floor in these areas. And so when we date the oceanic floor in these areas, what do we see? Well, let's go to our next diagram. So here we go. So this is the Juan de Fuca Ridge, which sits off the western or northwestern coast, should I say, of the United States. So we've got, California, we've got coming up into Oregon, Washington State, and then up into British Columbia in Canada. And so you can see the divergent plate boundary here is once again marked out by these thick dashed black lines. And you can see that either side of these divergent plate boundaries, you will see the same units repeating. So for instance, if we look, we can see that we have a divergent plate boundary here. You can see we have this thick band, then we have this much thinner band here. We can see that band repeated there. Then we have this thick band of this kind of yellow-orange color. We can see that thick band repeated here. Then we have this band of this lighter yellow-orange. We can see that repeated here. So you can see we have these bands of magnetic polarity mirroring each other either side of the divergent plate boundary. So this straight away tells us that new oceanic crust, which is forming at the divergent boundary, is being pushed away from it every time a new pulse of magma comes up along the divergent boundary to form new oceanic crust. So on top of that, just to really drive the point home, when you look at the age of the oceanic crust, you can quite clearly see that it's, it's younger, so it's got a present day age right here at the ridge. And as you move away from the ridge, the age of the crust increases. So by the time you're out over here towards the edge of the diagram, you're looking at something that's about 11 million years old. So over time, you can see that crust is created at the divergent plate boundary, and then it's pushed laterally away from that divergent plate boundary. Okay, so question 1. So explain why the belts of magnetic polarity either side of a divergent boundary are symmetrical. Well, I think we just covered that, so hopefully you can put together a 1 or 2 sentence answer to explain what's going on. So in question 2, we're going to look at figure 3.3. So if we come down to 3.3, here we go. So this is a schematic cross-section of the Mid-Atlantic Ridge. And so what you can see is obviously we have our Mid-Atlantic Ridge right here. So this is our area of elevated terrain right there. And you can see either side of it, we have these flatter areas that represent the abyssal plain, the relatively flat seafloor. So marked on the diagram, you can see in dark grey, we have the bands of normal magnetic polarity. So that's like the present day. And in the lighter grey, we have the bands of reversed magnetic polarity. So that's essentially the reverse of the modern setup. So you can also see that these bands of magnetic polarity are actually being used to split the oceanic crust into separate units. You can see one here, one here, one here, and one here. And then finally on this diagram, you will see we actually have an age scale down here at the bottom. So you can essentially approximate the ages of each of these boundaries. And you can also see that we have a scale bar up here in the top right of the diagram. So for question 2, we're looking at figure 3.3, and we're going to look at the magnetic polarities displayed by the seafloor surrounding the Mid-Atlantic Ridge. What was the magnetic polarity at the start and end of the Gauss? Okay, so the Gauss starts about 2.59 million years ago and ends about 3.59 million years ago. So if we come down and we look at our diagram, can we find it? Yes, here's the Gauss right here. You can see it's starting here at about 2.59 and it's finishing here at about 3.59. So the question is, look at the diagram. At the start and end of the Gauss, was the magnetic polarity normal or reversed? And so just if you're a bit uncertain about what these colors mean, just read the little point down here as part of the explanation of the diagram. Okay, so for question 3, we are going to calculate the rate of spreading in centimeters per year. Now this is important. Remember, the unit is centimeters per year. That means you have to turn any distance measurements you have into centimeters. Okay. So if we look at the diagram here, we can see the scale bar is in kilometers. So one of the things you're going to have to do is you're going to have to take that measurement, which you'll eventually calculate in kilometers, and convert it into centimeters. And the same thing is going to happen with the age, which is in years. Obviously, if you look at the scale bar down here, you can see it's in millions of years. So what you're going to have to do is you're going to have to convert that into years before you can actually calculate your rate. So try and make your life easy. I've actually provided a theoretical example for figure 3.5, which is this one right here. So as you can see, it's the same diagram as you have in figure 3.3. And I'm actually going to zoom in just to make the diagram a little bit larger. Here we go. Okay. So in this worked example, what are we going to do? Well, we are going to try and calculate the rate. And the first thing we're going to do is we're going to pick a point on our diagram. And so in this case, for instance, I've decided to pick a point right here. Okay, and I've given this point an age of 4 million years. Now, as you can quite clearly see, this does not correspond to the age scale at the bottom here. That's because this is a purely made up number that I'm using for my example calculation. You can also see that as part of this, I have measured the distance from the spreading ridge right here to the location that I selected, and that distance is 5.5 centimeters. The other thing is that I've also measured the length of my scale bar, and I've measured the length of my scale bar at 10 centimeters. And I know my scale bar actually represents 100 kilometers on the diagram. So what I need to do is I need to take all this information and use it to calculate a rate of spreading. How fast is the divergence taking place? So the first thing I'm going to have to do is I'm going to have to convert this scale bar into a measurement that I can use on my diagram. So to make things simple, what I'm going to do is I'm going to say, right, how much does 1 millimeter on this diagram represent in kilometers? So I'm going to calculate that by saying, right, so I know my scale bar is 10 centimeters in length. So I'm going to multiply that by 10, and that's going to give me the length of the scale bar in millimeters, so 100. All right, so I know that my scale bar is worth 100 kilometers, and I know that the distance from here to here is 100 millimeters. So if I take the distance in kilometers, 100, divide it by the length of the scale bar in millimeters, 100, that means that 1 millimeter on this diagram is equivalent to 1 kilometer. So that means, for instance, if I measure 5 millimeters, it means I'm measuring a distance of 5 kilometers. Now, once again, I'm just going to say this. These numbers that I'm dealing with here are made up. They are not real numbers. So, okay, so stage 2 is to establish the distance from our rift valley, which is this area right here. So here's our rift valley with our divergent plate boundary marked by the dashed white line. And I need to know the distance from there to the point on the seafloor that we've chosen, which is this point right here. Now, obviously, I've measured it with a ruler, and it's given me a made-up distance of 5.5 centimeters. All right, so first thing I'm going to do is I'm going to convert that 5.5 centimeters into millimeters. So I'm going to take 5.5, multiply by 10, gives me 55 millimeters. Now, I know that for each millimeter on my diagram, it's equivalent to 1 kilometer. So I can therefore calculate that the distance from the ridge here to the point where I'm measuring is equivalent to 55 kilometers of distance. Now, remember what I said earlier, we need to take that distance in kilometers and we need to convert it into centimeters because our rate is going to be in centimeters per year. So here we go. So obviously we know we've got 55 kilometers. We're going to multiply that by 1,000, and that's going to give me the distance in meters. So in this case, 55,000. I'm then going to take that distance in meters, multiply it again by 100, and I'm going to get the distance in centimeters. So the actual distance from the spreading ridge here to the point of the seafloor, which we are measuring from, is 5.5 million centimeters. The final thing we need to know then is the age at the location that we are measuring to. Well, you're going to get that from the scale bar. Okay. I should also point out, by the way, that the boundaries for each of these different portions of the seafloor actually have assigned ages to them. So if you look at the Gauss here, you can see it says 2.59. So this line right here is going to represent 2.59 million years ago. This line right here is going to represent 3.59 million years ago. So picking the start or end of one of these portions of the seafloor is actually quite a good way of setting the date that you'll be using. Okay, so for stage 3, we're going to calculate our age in years. So in my made up example, the age at this point is 4 million years. So I'm simply going to do 4 multiplied by 1 million gives me 4 million years. Done. And then the final stage is simply to calculate the rate. So I'm going to take my distance in centimeters, 5.5 million. I'm going to divide it by my age in years, 4 million, and that's going to give me a rate of 1.375 centimeters per year. And that's the rate at which new crust formed at our divergent plate boundary is being pushed laterally away from that divergent plate boundary. Okay, so the final question is question 4, and this is to calculate the ages of the basalt at points A and B. So if we come up here to diagram figure 3.3, you can see here is point A and here is point B. Now, the first thing I'm going to notice is that these points do not fall at a location where you can easily date them. So, for instance, they don't fall at the start or finish of one of these areas of the seafloor, and they don't fall on one of these clear ages here. So we're going to have to work out the age of these areas. We're going to have to try and accurately calculate it rather than guessing. Now, the first thing I will say is that when you look at these locations, you can kind of generally guess about where your age should be. So if we look at location A, you can probably say the age is going to be somewhere around maybe 2.8 to 2.9 million years, but you want a more exact number than that. So how are we going to achieve this? Well, it's actually relatively straightforward. So the first thing you're going to do is you're going to calculate the distance from the spreading ridge to point A or point B. So remember, you're going to have to calculate two different calculations, one for each location. So you're going to take your ruler, you're going to measure the distance from here to point A. I do apologize for looking at the wrong diagram there. Here we go, let's try this again. You're going to measure the distance from your spreading ridge here to point A, and from your spreading ridge to point B. And obviously you're going to take that distance in millimeters, and you are then going to convert that into a distance in centimeters, just like you did for question 3. So you now have the distance from your spreading ridge to your location, in this case point A, and in this case point B. So okay, so we have our distance, and then we're going to simply divide our distance by the rate that we calculated for question 3. So in my example, that rate was 1.375 centimeters a year. And so all you're going to do is you're just going to show me you're working to calculate the distance from the divergent plate boundary to location A and from the divergent plate boundary to location B. And then once you've calculated that distance in centimeters, you're then going to simply divide that number in centimeters by the rate that you calculated for question 3. And that is then going to give you the age for location A and also the age for location B. And so this is one of the ways in which geologists can estimate the ages for the oceanic crust in a certain area without having to go down there and actually drill samples and take them to the lab, which does cost a lot of money. Now, you're probably thinking, well, is that accurate? And the answer is, we'll discuss that more in part 2. But we've been going on for about 20 minutes now, so this is probably an excellent time for you to stop, get up, have a quick walk around, get yourself a glass of water, and then come back for the second half of this video.